So the first step is just going to be to download everything from that Google Drive folder. And I would recommend putting it on your desktop or somewhere else that's easy to access. Alright, so before we start our tutorial, I just wanted to kind of show some of the files that are in this folder that you downloaded. So we're in the OpenFoam simulation 3D geometry, and this is the pre-geo folder. So this is before we run any of the geometry, before we import our STL file. So when we open it, we have our 0 folder, constant folder, and system folder. So 0 obviously has a lot of initial conditions. Constant has some features like the actual polymesh, and we're going to put our geometry in there. It also has transport and turbulence properties. For our model today, we'll be using the K omega solver, so K omega SST, and the initial condition files that go with that model are K, nut, omega, P, and U. In addition, we have in this folder, we have our system, and this has our FV solution epi schemes, and that helps us with convergence. And then we also have snappy hex MeshDict and surface feature extractDict. So these are really important for when we actually import our STL file, when we want to run our simulation on that.
Alright, so there's some basic steps to today's tutorial. First, the category in green, those steps are all involving making our geometry, putting it in the right folder, and then finally actually running the geometry using the OpenFoam terminal. Then the red category, that's more about moving some of our geometry around into different folders within our actual file explorer. We have to delete a couple files after that step, and then we'll check our initial conditions. And then finally, the category in blue, which is just one step, it's step 8. It's actually running our simulation. So that's what we're going to be doing very last, and then we'll look at our results. So real quick, just a couple things you want to think about before you make your 3D geometry is you want to keep an eye on where your origin is, both in SolidWorks and then what it's going to be in Parafoam. You want to think about where your block mesh is going to be around your object, and that'll help you come up with where you want your vertices to be. And finally, you don't want to make your block mesh too small. The ratio between the cross-sectional area of your object to the block mesh should be about 1/10. So those are some steps that you should keep in mind.
Alright, so this is the geometry that's already in that folder. So you'll notice that we're in meters, just because it makes it easier when you're making your block mesh. A couple things to keep in mind. You're welcome to make your own geometry to import into this tutorial. You just want to keep it a couple little hints. One of them is make sure your object's centered about the origin. It'll make it way easier when you have to adjust your block mesh. Another thing is just keep track of your dimensions. It's really simple, but it can lead to big problems if you don't keep track of how big this is in respect to your block mesh. And then finally, just try to keep an idea of where your inlet flow is going to be coming from. You can use this coordinate system, which matches pretty nicely with the OpenFoam coordinate system. And yeah, that's about it for the tips. So if you do decide to make your new geometry, the place you're going to want to save it is first off in SolidWorks, you go File, Save As, then you go into the pre-geo folder, Constant, and this new folder, which isn't in other OpenFoam simulations, it's called Try Surface. And you're going to want to save your file in 2 ways in this folder. One is just as your regular SolidWorks part, so you can go Save. And I would recommend using the same name cylinder, just will make it easier later on in the tutorial. So once that saves, you'll go again, File, Save As, and we're still in that Try Surface folder. We're going to save it this time as an STL. So for your STL file, you'll want to make sure that it's saving in ASCII format. So that's good. Press OK, and then we'll also save it there. And we know it already exists. Again, you can change the name if you want, but you're going to have to go through and change all of the other names in whether it's the 0 folders or elsewhere. So I'd recommend just keeping the name cylinder. Even if it's not a cylinder, it's fine.
Alright, so before we run our geometry, we just want to double check a couple things in our folder. So we just want to make sure that in the tri-surface folder, we have our two files. We have our 3D object file and our STL file. In addition, we want to make sure that our block mesh accurately captures this 3D object. So my cylinder is 15 centimeters in diameter and 40 centimeters tall. So in our block mesh, everything's in meters. And based on that, with these vertices, we should be able to accurately capture our 3D object. We'll also keep an eye and take a look at what our boundaries are. So I basically made an inlet, outlet, front and back, and regular walls. So there's 4 walls and then an inlet and an outlet. So we'll be using those later in our boundary conditions. Finally, we want to just double check in our system folder for snappy hex mesh. We want to both be able to see our 3D object and our whole block mesh. So what you'll have to do is make sure that you define a point in location in mesh to make sure that this is a point that lives within your object, and therefore you'll be able to see both of them when you accurately snap your do snappy hex mesh. Alright, so it looks like we're ready to run our geometry, so that's pretty exciting. So what we're going to do first is we're going to make a copy of this pre-geo folder, and we're just going to paste it right there. But we're going to name this post-geo because we're actually going to run this bad boy. So next we're going to open up this folder in terminal, and you're going to use this chain of commands within terminal. So once it loads, you're going to run 3 different commands. The first one is just block mesh. So this is generating the actual block structure around our 3D object. Next, you're going to do for surface feature extract. And so that's taking the surfaces off of our 3D object. And then finally, you're going to use snappy hex mesh. And this one will take a little bit longer to run. But once we do that, we should be able to open it up in SimpleFoam and see what we have. Alright, so we are officially snapped. So it's time to open it up in SimpleFoam and see what we have. So it took us about 30 seconds to snap it, but it's not too bad. Alright, so once we open it up in SimpleFoam, we're just going to go apply. And then to make it easier to see, we're going to go for the wireframe. So you can see that Snappy Hex Mesh did a good job here. So we have our block mesh, which is surrounding our object, and then we have our 3D object right there sitting on the bottom of our box, just like we wanted. Alright, so this next part, we're going to capture our geometry that we just snapped, but we're also going to prepare our folder so that we're actually ready to run our simulation. So the first step, what we're going to do is we're going to take post-geo, which has our snap geometry, and we're just going to copy-paste it right in this folder here. And then once that's copy-pasted, we're going to rename it. Alright, so we're going to rename this folder, and we're going to name it Run, because this is the folder we're going to run later. Alright, so within Run, you see we have 0, 1, and 2. So 0 has initial conditions still. 1 and 2 are like the snap geometries, each iteration. So what we're going to do is we're going to go into 2. We're going to take this polymesh folder. So we're going to copy that folder. And we're going to delete this polymesh folder in constant and replace it with that polymesh folder from 2. So you take the polymesh from 2 and you replace the one in constant with that polymesh folder. So now we have our snap geometry in our polymesh. So now we're going to go back to our run, our overall folder, and we're going to delete folders 1 and 2. Alright, so now it's almost ready to run. Alright, so before we run our simulation, we just want to double check our boundary conditions and maybe adjust them if we need to. So we're going to go into the run 0 folder, This is always a good idea just to double check before you run. And also, so we're going to open up our U, which is velocity folder. So one thing I want to point out is when you're using like a snapped 3D geometry, you're going to have to define an additional boundary condition that wasn't in your original block mesh, and that's going to be just whatever you named your file. So in our case, we named it cylinder. That's why I had you name your 3D object cylinder earlier. It makes life a whole lot easier, and you don't have to adjust a zillion files later on. So in our case, we have cylinder as one of the boundary conditions, or boundary fields. And so anyway, so for the U file for our little tutorial, we're going to change this value at the inlet. Instead of just 1 meter per second, we're going to bump it up to 5 meters per second. So you don't have to do that, but it shows that you can easily go in and adjust before you run a simulation. And if you ever get confused about like what inlet, outlet, some of those boundary fields are, you can always go back. This is why we make so many folders. You can always go back to your pre-geo folder, constant, polymesh, into your block MeshDict. And this will show you, kind of explain further what you originally defined as your inlet, what you defined as your outlet, and it helps you visualize what's going on a little bit better at the boundaries if you get confused. Alright, so I think now we're ready to rock. So what we're going to do is we're going to make a copy of our run folder. And at this point, you might want to name your original run folder something like pre-run instead. We probably should have done that originally, but I didn't really think about it. So now we have a pre-run folder. And this one we're not going to actually touch in terminal. This run copy, though, we're going to name this guy post-run. And so now we know that it's after we run it. So we're going to open it up in terminal. And of course it takes a minute to load. And now we're going to type in SimpleFoam. And it's going to run for quite a while. So grab a coffee and check back in the next slide. Alright, so you'll notice that for the sake of this demonstration, the simulation went to time 200. So the way you can change that if you want better convergence is you can go into, you can go into System and then Control Dict, and you can definitely feel free to play around with different end times and different convergences in other files. So, but for the sake of our tutorial, we just had it end after 200, so you wouldn't have to wait around all day for that. So now we're going to open up the results in ParaView. So I just typed SimpleFoam into the terminal. Alright, so now we're going to go, we don't want to skip 0 time, we're going to apply. Alright, and then so we can actually see our geometry inside, we're just going to click on wireframe. Alright, so this is the pressure, so you can see that we have the highest pressure right at the surface, which makes sense, that's our stagnation pressure. And if we want to look at our velocity, so you can see a little bit of what's going on for the velocity. So we set 5 at the inlet, so that makes sense with this key over here, the color map. And then you can also see that there's 0 velocity right when it hits, which also makes sense. And so yeah, so basically you can play around with your results and try to tweak some of your boundary conditions to get some different things. But overall, hopefully this was a pretty helpful tutorial. And